Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com.
Hello, everyone.
Today we are opening Unit 6, that is electromagnetic induction, and we are going to attack probably the most tricky topic in this chapter.
Oh, let me guess. Lenz's law.
Lenz's law and the law of conservation of energy, yes.
That topic is always confusing me. Especially that negative sign in the formula. It seems like such a small thing, but I know I always lose marks on it.
So no worry. By the end of this audio, we will make this topic really simple and, exam safe. You will never lose marks on that negative sign again, I promise.
Okay, that's a big promise. I'm ready to learn.
Okay, so let's start with a simple question, just to build our intuition. Imagine you're holding a copper ring, just a simple closed loop.
Okay.
And you drop a strong bar magnet, say North Pole first, towards it. Does it fall like a stone, or does something invisible try to stop it?
I have actually seen this in a video. It falls so slowly, like it's floating in honey or something. It looks very strange. Is it magic? Or maybe friction?
It's not magic. It's pure physics. And it's not air friction also, because if you dropped a piece of plastic, it would just fall instantly.
So what is stopping it then? There's nothing touching it.
It's the same force that can actually make a ring float. There was this famous example of the levitating ring.
Levitating?
Yes. If you place a copper ring over a coil with AC current, the ring actually floats in the air. It just hangs there, defying gravity.
Wow. That sounds amazing. But why does it float?
Because the coil and the ring are basically fighting. The force that makes it float is the exact same reason behind the minus sign in Faraday's law. Nature's being very stubborn here. Let's find out why.
Okay, I am listening. Why is nature so stubborn?
In the previous topic, we learned Faraday's law, correct?
Yeah.
We know that a changing magnetic flux produces a current.
Yes. Change in flux creates induced current. That part is clear.
But Faraday's law only tells us the magnitude, how much current. The big question is, what is the direction of that current?
Is it clockwise? Is it anti-clockwise?
Exactly. Does it help the magnet or does it fight the magnet?
I usually just guess in the exam. Or I try to use the right-hand rule and, get confused.
No more guessing. Here is the core idea. The induced current is not random. It has only one job. Its job is to oppose the change that created it.
Oppose the change? What does that mean exactly?
Think of the coil like a very, very stubborn person. Or, an even better analogy is the traffic crowd. Imagine a room that's full of people, like a packed train compartment.
Okay, I can imagine that. Very packed. No space to move.
Now, suppose you try to push more people into that room very quickly. You are increasing the crowd, increasing the flux. What will the people inside do?
They will push back, of course. They'll shout, "No space, don't come in." They'll try to stop me.
Exactly. They repel you. They oppose the increase. Now imagine the opposite. You're inside with your friends, and someone tries to pull you out quickly. You're decreasing the crowd.
Well, if they're my friends, they might grab my hand and say, "Don't go, stay here."
Correct. They're trying to keep you inside. They oppose the decrease. This is exactly how a coil behaves.
So if I try to add magnetic flux, it pushes back.
Yeah.
And if I try to remove the flux, it pulls it back.
Yes. Let's build a proper mental image. Imagine a north pole of a bar magnet moving towards a coil. The magnetic flux is increasing inside that coil.
Okay, North Pole coming closer, flux increasing.
The coil hates this change. It wants to stop the North Pole. It wants to repel it. Now, you tell me, how can a coil repel a North Pole?
We know that, poles repel, so the coil must become a North Pole as well.
Perfect. Absolutely perfect. The face of the coil that's facing the magnet becomes a temporary North Pole. The current starts flowing in just the right direction, anti-clockwise, to create that North Pole face. North repels north.
Okay, I understood that. It puts up a sort of shield to stop the incoming magnet?
Exactly. Now let's imagine the second part. You are pulling that North Pole away from the coil. You are taking it back. The flux is now decreasing.
And the coil hates this change also.
Yes. It's very attached to how things are. Now that the magnet is leaving, the coil wants to stop it from leaving. It wants to pull it back.
So it needs to attract the magnet now.
Yes. And to attract a leaving North Pole, what must the coil become?
Unlike poles attract. So it has to become a south pole.
Correct. The current direction instantly reverses. It becomes clockwise. This creates a temporary south pole to pull that magnet back.
Wow. So the coil is very contrary. Whatever I do, it does the opposite. If I come near, it says go away. If I go away, it says come back.
It is the most stubborn thing in physics. It fights the increase and it fights the decrease. This behavior is what we call Lenz's law.
That's actually quite simple logic. It's just opposition.
Now let's see how insert defines this rule. We need the formal wording for the board exam. Could you please read the statement from Source 1, Section 6.5?
Okay, reading it now. The polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it.
Right, and that key phrase, opposes the change in magnetic flux. That is our stubborn crowd.
And this connects to the formula.
Yes. Look at equation 6.3 in the insert book. Epsilon equals minus d phi by dt. You see that minus sign?
Yes, it's right there at the front.
That negative sign is Lenz's law. That little dash represents this entire concept of opposition. If that sign wasn't there, the whole universe would break.
The universe would break. That sounds very dramatic for a physics equation.
It's true. It's not just math, it's fundamental. But before I explain that, a quick reminder, hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com.
Okay.
Right. Back to the broken universe.
Yes, please tell me, why is the minus sign so important?
This brings us to the conservation of energy proof. This is a very common 3-mark question in the exam. Show that Lenz's law is in accordance with the law of conservation of energy.
Ah, yes. I always get stuck on this proof. I never know how to start the answer.
The best way is to imagine the opposite. Suppose the coil did not oppose the magnet. Let's imagine a friendly coil for a moment.
Okay, a friendly coil.
You push the North Pole towards it. The flux increases. Now, instead of repelling, suppose this friendly coil attracts the magnet. It says, come here. What happens to the magnet?
If the coil attracts it, the magnet would, well, it would get pulled in faster.
Yes. And because it moves faster, the flux changes faster, correct?
Yes. Faster movement means a faster change in flux.
And according to Faraday's law, if the flux changes faster, the induced current gets
stronger. The current gets stronger.
And if the current gets stronger, the magnetic attraction gets even stronger.
So it would pull the magnet even faster.
Oh, exactly. You see the loop? You give the magnet a tiny push, and the coil pulls it faster, which makes more current, which pulls it faster. The magnet would just accelerate infinitely.
It would just keep speeding up forever on its own.
Yes. Without you doing any extra work, you'd get infinite kinetic energy from a single small tap.
That sounds completely impossible. That's like a perpetual motion machine.
Correct. And that violates the law of conservation of energy. You cannot get energy for free. It can't be created from nothing. This is why the friendly coil is impossible.
I see. So if we want electrical energy in the coil, we have to pay for it somehow.
Exactly. You have to pay the bill. And how do we pay?
By doing work.
Yes. With mechanical work.
Yeah.
Because Lenz's law says the coil repels you, you have to push hard against that repulsion. Your hand has to apply a force. You are burning calories to push that magnet against the coil's will.
So my hand doing the pushing, that work I'm doing.
It is not disappearing. It is being converted. The mechanical work you do against that repulsive force is converted, joule for joule, into the electrical energy that flows in the coil.
Oh, so the current is literally the work I did, just in a different form.
That is the beauty of physics. The opposition is what makes you do the work. No opposition, no work. No work, no energy. Impossible.
That makes total sense now. The fighting is just the cost of generating power.
That's why we say Lenz's law is a consequence of conservation of energy. So Faraday gave us the magnitude, and now Lenz gives us the direction. Together, there's a complete package.
Okay, I am feeling confident. Oppose the change. Conservation of energy. Got it.
Now, don't get too confident just yet. Pay very close attention. There's one mistake, a silent killer mistake, that cuts marks in board exams every single year.
What mistake? Tell me quickly so I can avoid it.
Many students memorize that Lenz's law means the induced magnetic field is always opposite to the external magnetic field.
Wait, isn't that what we just said? North repels north, so the fields are opposite.
In that one specific case of the magnet approaching, yes. But listen carefully. Students confuse opposing the change with opposing the field. They are not the same thing.
I'm confused now. What's the difference?
Let's take the second case again. The North Pole is moving away. The external field from the magnet is pointing into the coil, but it's getting weaker, correct?
Yes. The magnet is leaving, so the field inside the coil is getting weaker.
To oppose this decrease, this weakening, the coil needs to support the field. It needs to try and keep it strong.
So the coil creates a field in the same direction as the external one.
Yes. To attract the leaving North Pole, it becomes a South Pole. The induced field lines from the coil now point in the same direction as the magnet's field lines. It's trying to prop up the dying field.
Wait a minute. So if the external field is decreasing, the coil actually helps the field.
It helps the field to stop it from changing. It's like a friend holding you up when you're about to fall. It resists the change.
So it doesn't always fight the field's direction.
No, it always fights the change. If flux is increasing, it fights the field, making an opposite field. If flux is decreasing, it supports the field, making a field in the same direction.
That is a very tricky difference. I can see why students get that wrong.
This is why you must remember the hook. Oppose the change, not the field. Write that down in your notes right now.
Writing it down. Oppose the change, not the field.
Good. Now let's lock this into your memory. We need a memory anchor.
Yes, please. Give me a shortcut to remember this.
First, a simple phrase. Lenz, a minus sign.
Lenz, a minus sign. That's catchy. I like it.
And for the concept, just remember, nature dislikes sudden change.
Like my grandmother. She also dislikes sudden change. She likes everything to stay exactly the same.
Exactly like that. The coil is a strict grandmother. Now, a physical gesture. I want you to do this right now.
Okay, what should I do?
Push your palm forward against the air like you're pushing something heavy. Feel that imaginary resistance.
Yes, I'm pushing forward. I can feel it.
When you push forward, imagine a force pushing back. That feeling of resistance. That is Lenz's law.
Okay, push forward, feel the pushback.
Now imagine grabbing a handle and pulling your hand back quickly. Imagine it's sticky, it tries to pull you forward.
So when I pull back, it tries to keep me there.
Exactly. Use this gesture in the exam hall if you get confused. Pushing in is opposed, pulling out is opposed. It always resists your motion.
I might look a bit funny doing hand gestures in the exam, but if it gets me marks, I'll do it.
Marks are what matter. Okay, quick test. A south pole of a magnet is falling towards the coil. What does the top face of the coil become?
Okay, let me think. South is coming closer. The coil wants to stop it. To stop a south pole, it must repel. So, south repels south. The face becomes a south pole.
Perfect. Now, that same south pole falls through the coil and starts moving away from the bottom. What does the bottom face become?
Okay, now, south is leaving from the bottom. The coil wants to stop it from leaving, so it needs to attract it back. To attract a south pole, it needs a north pole. The bottom face becomes north.
Excellent. You have mastered it.
It's actually quite fun once you get the logic. It's like a game of opposites.
It is a game. And this connects perfectly to our next topics, like motional EMF and generators.
Does this also explain why we need big engines to run electric generators?
100%. That's a great connection. In a generator, you're spinning a coil. The induced current creates magnetic field that tries to stop the coil from spinning.
So the generator is actually fighting against the engine.
Yes. The more electricity you draw, the harder it is to spin. You need fuel to do work against Lenz's law to make that electricity.
It's all connecting now. It's all conservation of energy.
See, no magic.
Okay.
Let's summarize everything into 3 bullet points for your final revision.
I'm ready with my pen.
Point number 1. Lenz's law gives the direction or polarity of the induced current.
Direction.
Point number 2. The direction always opposes the change in magnetic flux. Remember the hook. Oppose the change, not the field.
Opposes the change. Got it. Check.
And point number 3. This law is a direct consequence of the law of conservation of energy. Mechanical work done becomes electrical energy.
Work done equals electrical energy. Check.
If you rate these 3 points and draw the diagram, you will get full marks.
I feel so much better about that negative sign now. It's not just a math symbol. It's a physical law.
It's the force of nature maintaining balance.
Thank you so much for clearing this up.
Anytime. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com. We have full notes, solved examples, and more explainers just like this.
I will definitely check it out.
Keep practicing, and do not fear the minus sign.
See you in the next topic.